Okay, hello everyone. Good afternoon. Good afternoon, everyone. And welcome to the last tutorial session for this semester. Okay, so we have arrived at the last tutorial session for this semester. Looks like most everyone is here. Okay, let me take your attendance first before we start. Okay, uh, check. All right. Hu Hing Dong. Hu Hing Dong. Good afternoon. Lu Jui Min. Right. Ng Han Xiang. Ng Wei Hong. Ng Wei Hong. Ong Mei Lin. All right. Peng Xuewen. Peng Xuewen. Peng Xuewen. Hua Yihan. Okay. Okay. So Yan Cheng. Right. Tan Xin Shen. Okay. Teo Leong Ho. Teo Yi Si. Teo Yi Si. Okay. Wong Chung Yi. Right. Wong Ka Sing. Wong Ka Sing. Okay. Yong Wing Liang. Right. And Yong Qie. Yong Qie. Okay. Ng Wei Hong, are you here? Ng Wei Hong. Ng Wei Hong. Wei Hong. Wei Hong. Okay. Wei Hong is not here. Huh? Right. So we will continue. We will continue with now. Um, just to repeat again. I think I mentioned this, but I just repeat it again. So your final exam, you have four questions. First one is on architecture, right? Architecture, processor, assembly language, programming, interrupts, and memory lah. So you are given some practice in tutorial 3 and 4. Okay, tutorial 3 is on CPU, interrupts, assembly language. Tutorial 4 is on memory. So tutorial 3 and 4 gives you some exercises for question 1, architecture. And I also gave you some open-ended exam type questions already lah. Okay, then question 2 on software development, right? You have some exercises in tutorial 2 for this. Tutorial 2 is on software development. Okay. Then question 3 is on RTOS. So exercises for question 3 is on tutorial 5. Okay, and we have looked at tutorial 5 already. I've given you one exam type question. So I'm going to give you another exam type question for RTOS. And then we will wrap up by looking at question 4, system design. So system design, you will have some examples and exercises in tutorial 6. Okay. Now, tutorial 7 is not covered in your exam. Okay. Tutorial 7 is in our syllabus, but it will not be assessed because tutorial 7 is on the current state of the art technology of microcontroller peripherals. Tutorial 7 will be exercises for your week 14 lecture notes. Okay, next week we will have no lecture videos. So please come for the lecture on Tuesday, right? Your Tuesday the 2 hours lecture, please come, right? We're going to have a live session for revision, Okay, no lecture videos. Now the lecture notes for IoT MCU, the lecture notes for IoT MCU is uploaded here. Okay, these are the lecture notes for IoT MCU. Okay, week 14 lecture discussion. So in this IoT MCU, the IoT MCU are the features of microcontrollers which support the implementation of IoT, right? So your microcontroller needs a lot of peripherals to support the implementation of IoT. The main peripherals are the analog, ADC, DAC. For timing, you got timers. For communication, you got the serial ports. And for to speed up bulk transfer of data, you got DMA. So these are all covered here. And exercises are given in tutorial 7. Okay, but this week 14 lecture discussion and the tutorial 7 is not in your exam. Okay, this is just for your knowledge. All right. Also, the week 13 lecture discussion, right? This week you watch some lecture videos on IoT. Those are very conceptual, because actually IoT is concept only, right? The technical part of IoT you already learned. The technical part of IoT is how to program and use microcontrollers, right? The heart of your IoT device is actually a microcontroller. And the only new thing that you add in is a Ethernet module. Because in order for your IoT device to be considered an IoT device, it must have connection over the internet with another device. Okay? IoT means communication between things over the internet. For example, your smart refrigerator communicate with your smartphone, an app in your smartphone through the internet. So your fridge run out of something already, your fridge will then tell your app in your smartphone. Right? So it's actually the things communicating with each other. And in order for this communication to happen, you just need to add one more module, one more communication module to your microcontroller, and that is the Ethernet module. If your microcontroller don't have a built-in Ethernet peripheral, then you need an Ethernet module. But your LPC1768 has a built-in Ethernet peripheral. Okay, it already supports. So you can directly connect the Ethernet cable to your microcontroller. Or if you cannot have direct connection, then you need wireless communication. Then you will need, instead of an Ethernet module, you need a wireless module. Okay, a wireless module. For example, a very cheap radio frequency transmitter receiver, or you can have a Bluetooth low power, right? Bluetooth low energy transmitter receiver, or you can have a Zigbee. That's a short range networking communications protocol. So you got many different types of wireless communication. And the concept we discussed here, okay, this is all very conceptual. So this one is actually very light reading. It's not technical. For example, what is an IoT? What are applications of IoT? What hardware do you need? What type of sensors do you need to make an IoT? Okay, and finally, the most important is connectivity. How do you connect your IoT device to the internet? Right. So there are many different methods. Okay. For IoT, normally is low power wireless area network. Cellular and satellite, these are more high powered. These are for bigger devices which have a bigger power source. Right. Normally means powered or a very big battery. For us, our small IoT devices, we will normally be uh, low power wireless area network WLP1. Okay, so this is all just conceptual. This will not be examined. This is not coming out in your exam. Okay. All right. So we will have a revision next week during our 3 hour lecture session. Okay, our 3 hours lecture session next week. We will discuss these 4 questions and also have a revision of your entire syllabus. Okay, and next week our lab session, the 2 hour lab session is consultation. So there is no lab, it's consultation. So I will be there during those 2 hours if you have any questions. Okay, so now coming back to tutorial 5 and 6. So we have this, I want to give you another exam type question, another exam type question on RTOS, right? Okay, so try this question now. So try this exam type question. Right, this is really straightforward. We will discuss at okay 4:30. Right. So again, this another example of a exam type question, not a full question. It's just 20 marks. So try this out, and we will see how you score. Right, then you will know whether you are prepared for the final exam or not. Okay. So please start now, and we will discuss at 4:30. All right, everyone. Okay, class. So let's discuss this question. Okay. Is everyone ready? Okay, everyone ready to discuss this question? Okay. Now, let's look at what this question wants. Okay, we need to write a program using CMSIS RTOS RTX to control two LEDs, LED 1 and LED 2, on LPC 1768. Okay, so you know that the LPC 1768 has four LEDs on board, LED 1, 2, 3, and 4. But we only need to use LED 1 and 2. So what do we need to use them for? Okay, let me draw a diagram here. You need to flash some LEDs. Okay, we need to flash some LEDs. So LED 2 needs to be flashed at LED 2. Okay, let's do LED 1 first. Okay, LED 1 needs to be flashed at 5 hertz, 50% duty cycle. So 5 hertz means 1, 2, 3, 4, 5. Okay, so this is 1 second. Okay, 5 hertz is 5 cycles per second. Okay, so how long is each one? Now, this one is 50%. 50% duty cycle means 50% of the time it is high. The remaining time is low. Okay, so this would be, if this is 1 second, then this would be 100 milliseconds, and this one is 100 milliseconds. So what would we need for this? Very straightforward. We will just need to use OS delay of uh, 100. So we have to make some assumptions. We need to assume we need to assume that the system tick is 1 millisecond. Okay, the system tick is not always 1 millisecond. It's configurable one. Okay, so we have to state our assumption. So in this case, we are assuming that the system tick is 1 millisecond. So this gives me 100 milliseconds. Okay, now how about LED 2? So LED 2 needs to be 2 hertz. So 2 hertz would be 1, 2. Okay, 2 hertz. This is 1 second. So 2 hertz would be 2 cycles per second. So how much is the time for each one? This one would be 1 second divided by 4, divided by 4. So this is 250 milliseconds, and this is 250 milliseconds. Okay, and all we need to create this would be OS delay of 250. Right? So now we know what we need to do already. Let's look at this code that is given to us. So we need to control LED 1 and 2. Fortunately, you don't have to write the library code. You don't have to write the API because the API is provided. Okay, so you got led.c, the source file, and led.h, the header file. This is your LED library or the API functions to access the LED. Okay, so you got three functions given here. Initialize LED init, initialize the GPIO port so that those four pins are outputs. Then you can select which one of the four LEDs to turn on using LED on. The input parameter is 1, 2, 3, or 4. You can select which LED to turn off. Input parameter is 1, 2, 3, or 4. Okay, so let's look at the code now. Let's look at the code now. Okay, so your answer should look like this. Your answer should look like this. First of all, you must have you must include the header file and the operating system library. You must have these two lines. Okay, so include the necessary files that will be 2 marks. If you have these two lines, it is 2 marks. Okay, and then you are asked to create two threads, one thread to control each LED. So you will need to declare the thread prototypes and define the thread parameters. So we declare the thread prototype. We got thread 1 and thread 2. Just declare 2, right? And then we define the thread parameters. So this is the name of the thread, follow the name of the function. This is the priority, number of instance, and stack size. Now the priority, you can put the same priority or you can put different priority. It doesn't matter. Why? If you put same priority, then they'll run round robin. No? If you put different priority, then the higher priority will always get to run, right? But that is not the case because we use OS delay. So even though, let's say, thread 1 has higher priority, right? Thread 1 should always run, no? But whenever it execute OS delay 100, it is going to go into a waiting state for 100 system ticks. So when this thread is in a waiting state, the other thread, although lower priority, will be able to run. So actually, you can specify any parameter, whether they are same or different, it will still be okay for this simple program. Okay. Now, the thread function prototype, notice that here, I always only put void, but here is place void constant star argument. This is because of actually the expected input parameter, the expected input parameter is a void pointer. This is a void pointer. Normally, you will say int star, integer, pointer to integer, or you will say char star, pointer to character, or you can say float, pointer to float, right? But when we use a void star, this means you can point to anything. You can point to an integer, you can point to a float, you can point to a character, you can point to anything. Okay, so this is a pointer to anything. And you give this pointer to anything, the name argument. Actually, you can use any name lah, right? They just use argument here. Okay, and then you can add a constant keyword in front, or you can add the constant keyword here. No difference one. So what's the purpose of the constant keyword lah? The constant keyword is just to ensure that this pointer is never modified. Okay, because when you write your program, especially if your program is very long, maybe at some point somewhere you accidentally modify this pointer. So your initial designer, you actually don't want to modify this pointer, but you may accidentally later modify it. So when you add the constant keyword, you're telling the compiler, please help me check and make sure that this pointer is never modified. So if anywhere in your program you modify this pointer, then the compiler will give you an error. It will tell you you are trying to modify a constant value. Okay, so that's the first implication if you put const here. The second implication is this pointer will be placed in code memory because the value won't change. So instead of placing it in the limited SRAM, it will be placed inside flash, your larger code memory if you use the constant keyword. Okay, this is only applicable for microcontroller programming. Desktop programming, the compiler rules may be different. Okay, all right. So because you declare this, the input is a pointer, and we are not giving it any value, right? So that's why when you create the thread, the value that you pass is null. Null means hexadecimal zero. It means you're not pointing to anything. Okay, which is why I put void is still correct because we are not passing in anything. So it doesn't matter. But you'll get a warning telling you if you put void, you get a warning saying incompatible input parameter. Right? So if you don't like that warning, you should put the complete input parameter, void constant asterisk. And this is just a name. You can put ABC. It's just a name. Okay, so if you have defined the thread parameters and the function prototype, this is 2 marks. Okay, and then correctly writing thread 1 function code, this is 3 marks. So writing your thread 1 function code, you just turn on the LED, delay, turn off, delay, and run forever. Okay, this is your forever loop. You can also put while one, no difference one. This one is an unconditional for loop. Unconditional for loop means it will loop forever because there are no conditions. It's the same as a while one, okay, forever loop. So if you code thread 1 correctly, it's 3 marks. If you code thread 2 correctly, 3 marks. So thread 2 would be delay of 250, right? These 3 marks. Okay, and then in your main function, you need to call the LED init to initialize the GPIO, and then you need to create the two threads. OS kernel initialize and OS kernel start, these two is not necessary because actually the kernel is already initialized and started because your main is actually a thread. The main function is actually the first thread. So actually the kernel has already been initialized and is running already. Okay? So all you need to do here is if you call the LED init to initialize the GPIOs, and then you create the two threads, that would be 2 marks, right? 2 marks. You create the threads here, 2 marks. So if you write any other programmer that do the same operation, it will be 12 marks, the full 12 marks. Okay. So I think this is pretty straightforward. Everyone should get full marks. And by the way, take note that in your exam, you can always simulate your programs. So in the exam, if you're given any programming question, it'll be rather short one. The program won't be more than 20 plus lines of code maximum. It will be a rather short program. You can always simulate your program to check whether your answer is correct or not. Okay. All right. So that's part A. Right? I hope no problems with part A. Now let's have a look at part B. Okay. Let's have a look at part B. So the question for part B is assess the usefulness of SVC function in an RTOS environment. Okay. Now SVC functions, what are they for? So uh, we have threads. We have in an RTOS environment, you have threads. But threads, they run in a so-called thread mode. What do we mean by thread mode? Thread mode means the thread uses the process stack and it has no privilege, right? Thread mode. Now, but the problem is we have system resources. We have system resources that needs privilege. You need privilege to access. Okay, so I don't care. Why do I care about these system resources? That's because example of system resources where you need privilege to access is, for example, your message queue. For example, your semaphore. These are all kernel objects, kernel or operating system objects. So kernel or operating system objects, right? They reside in your operating system memory. So these objects, these variables, right? They all require privilege to access because they are inside your RTOS memory. These are examples of system resources that need privilege to access. So your thread, you need to get something from the message queue. Your thread, need to the semaphore, but you need privilege. So what to do? Okay, then we make use of the SVC handler. The SVC handler, right? As do all handlers, run in handler mode. What is the characteristics of handler mode? Handler mode uses the main stack and it always have privilege. So any code running in handler mode will always have privilege. So what the thread does is the thread will trigger the thread will trigger an SVC exception. How does the thread trigger an SVC exception? Already seen this in week 4 lecture discussion. In week 4 lecture discussion, you have seen that you can mark underscore underscore SVC. When you add this keyword underscore underscore SVC in front of a function, you are defining that this function is an SVC function. So whenever the thread calls that function, you will trigger a SVC exception. Okay, so um, and each of those functions, right, can be you got your SVC exception has an input parameter. You can actually pass an input to SVC handler. The input parameter is a number from 0 to 255. So what's the implication of this? You can specify 256 different operations. Okay, actually lah, you trigger an SVC exception by making a function an SVC function. No? You can actually make up to 256 functions. Okay, you can make a 256. You can define 256 different functions as an SVC function. Okay, so when you call that function, the SVC handler will run that function for you. So when you trigger the SVC exception, the SVC handler will then run that function or that operation for you. And because SVC handler is inherently with privilege, okay, and so the SVC handler will then access the system resource for the thread. So what's the advantage of this? The advantage of this is the threads cannot do anything funny with system resources. If the threads want to do anything at all to the system resources, it will be one of the very well-defined operations, one of the maximum 256 well-defined operations. Okay, all these operations are legal and well-defined, and the threads can request the SVC handler to carry out these operations. Okay, the threads cannot simply go and do any of its own custom operation on system resources. Not possible. Okay, so this makes the system very secure, right? Okay, so assess the usefulness of SBC function in an RTOS environment. Well, this is how it works, right? So you can explain your answer using a diagram like this. Okay, so threads access system resources that require privilege using the SBC handler, right? Okay, or you can also answer in text form. So how do you answer in text form? Okay, if you answer in text form, it will be like this. Okay, answering in text form like this. So SVC functions, you need it in a secure RTOS environment. Okay, they are software interrupt functions because you trigger them using software. It's not hardware interrupt, it's software interrupt. Okay, and these SVC functions run in privilege handler mode. They can accept arguments and return values because if it's a message queue, your thread wants to get something from the message queue, then the SVC handler need to return the message, the 2-bit value, right? So you can, besides accepting arguments, you can also return values. Okay? Just like any normal function. The SVC handler is just like any function. Functions can return values, right? So SVC functions, they are used by task in unprivileged mode, task without privilege. They request the SVC to help them access protected peripherals. So another example besides these kernel objects is you want to configure uh, the core peripherals like the NVIC or the SysTick, okay, if it's necessary, lah. Right. So if you can describe the usefulness of SVC in RTOS environment, then it's 4 marks, okay, or any other description that is acceptable, okay, right? Any questions here? No questions, Okay, let's go to the last part of this question. Let's go to the last part, right? Let's go to the last part. Okay. Now, the last part of this question is, what is the value of OS thread set priority in the hard real-time system? Okay, so we need to explain some terms first. We need to explain some terms first. So first of all, what is a real-time system? So a real-time system, right? A real-time system is you need to respond within within a specific deadline. Okay, a real-time system is where you need to provide a response within a specific deadline. So what's a hard real-time system? Hard real-time system is a failure to meet deadline will be catastrophic, right? A hard real-time system means that if you fail to meet the deadline, the result will be catastrophic lah. Okay. How so? For example, fly by wire. Have you heard of fly by wire before? Fly by wire or is fly by wire or is you see last time the aircrafts the aircrafts the aircrafts last time not like this. The aircrafts last time their wings are very big one, right? And then they have a lot of this control. So these are control surfaces. Now these control surfaces, right, are controlled by the pilot. Okay, the pilot controls this, and the wings are very big so that the plane is very stable. And how the plane moves, the plane how the plane moves, right? How the plane moves and like this, how the plane moves is fully controlled by the pilot. Okay, but nowadays, you see the aircraft, the shape of the aircraft is like this, right? They can actually make an aircraft shape like this one. This is the cockpit, right? So such a weird shape is totally not aerodynamic one, not aerodynamic at all. But why they create this shape? Because of stealth, right? But it's totally not aerodynamic one. So a totally not aerodynamic design, now you put it in the air, it's going to be vibrating and shaking like crazy, right? But it seems that the plane is very stable in the air. Why? Because actually there's a lot of micro thrusters. So these micro thrusters, they release small amounts of thrust, small amounts of thrust of air to stabilize the aircraft. And all of these are automatic one. So you have a lot of sensors that is detecting the stability of the aircraft. So when aircraft starts to move out of the stable point, then all these tiny micro thrusters will provide micro thrust, small amounts of thrust to correct the position of the aircraft. So it's always very stable one. So we call this fly by wire. The pilot no longer controls everything. Now what happens if this fly by wire system, the thrust are not triggered correctly, they are late, then your whole plane will be vibrating and shaking like crazy, right? Or worst case, it will go out of control and crash. So that is catastrophic, right? Or there are a lot of things also. For example, you have the orbital correction system of a satellite. Your satellite is staying in a geosynchronous orbit because its position is constantly being corrected by micro thrusters. So if you miss the micro thruster, miss its correction, it's late, then the satellite is going to fall back to Earth. Catastrophic, right? Other more down to earth systems are, for example, your car, the anti-lock braking system, right? When it's raining, you're driving, your brakes might be stuck to your wet wheels because of water. So the brake pad is stuck to the wheels. Okay, the anti-lock braking system is supposed to release the brake that is stuck to your wheels. Otherwise, your car will go out of control. So if it's late by a little bit, then you also cannot control your car already. So all of these are catastrophic. Okay. Now, a soft real-time system, uh, failure to meet the deadline will just failure to meet the deadline will not be catastrophic. It will just inconvenience the user. Okay, if you fail to meet the deadline, the user will just feel inconvenience. Like at all those machines, you press a button, it's supposed to do something, but sometimes it's late, maybe 1 or 2 seconds. Then you say, "Hey, why is so slow on this machine lagging already?" But no, nothing catastrophic lah. No? Okay. Um, so hard real-time system, hard real-time system. Why do we need this? Why do we need this OS thread set priority? So this OS thread set priority is to change thread priority during runtime. Okay, so why do you need to change thread priority during runtime? Okay, here is an example. So you say, what is the value of OS thread set priority in hard real-time system? So why do we need to change thread priority during runtime for real-time systems where failure to meet deadline will be catastrophic? So An example will be you have a low priority thread. A low priority thread is using a shared resource that is needed by a high priority thread. So you got a low priority thread is using a shared resource that the high priority thread needs. So the high priority thread needs to wait until the low priority thread finish. Okay, just wait a bit. But, but then the problem is, but a medium priority thread preempts the low priority thread. Okay, uh, what is worst? What is worse? What is worse? Worse is if the medium priority thread takes relatively long time to run. So what happens is, if a medium priority thread preempts the low priority thread, then the high priority thread will now not only have to wait for the low priority thread, it has to wait for the medium priority thread. Okay, and this medium priority thread might take relatively long time to run. So definitely you're going to fail to meet your deadline, right? So what the high priority thread can do is, the high priority the high priority thread can temporarily raise the priority priority of the low priority thread. Okay, using OS thread set priority. So that's one of its use. The high priority thread can temporarily raise the priority of the low priority thread using OS thread set priority. Okay, we make the low priority thread high priority so it can finish very fast, so that it can finish quickly and allow the high priority thread to continue execution, right? So this is one example. Of course, you can think of other examples why you need to change thread priority during runtime. Okay, right. So you can write like this, or I think this one is probably saying the same thing. Okay, it's saying the same thing, right? So it's called priority inversion. It's actually the same thing. When you have a high priority thread that is delayed by a medium priority thread, okay, this is called priority inversion, where the high priority cannot run. It's being blocked by some lower priority threads. Okay? The OS thread set priority function can allow the higher priority thread to temporarily raise low priority threads. Okay, that the high priority thread is waiting for. Okay, I think this is a better explanation. This one not so clear. Okay, all right. So you have to understand how the RTOS works to answer these questions. Okay. All right. Do you have any questions on this RTOS past exam type question? Everyone okay? All right. Now I think it's pretty straightforward lah. So let me just give you a quick look at design type questions. Design type questions. Let me just give you a quick look at at system design questions. Okay, let's just have a quick look. So system design question, tutorial 6. Let's have a quick look. Tutorial 6. Oh, not this one. I think it's here, tutorial 6. Okay, yeah. Okay, let's have a quick look at one of the. Okay, let's say here, question 5. I think this is a full exam question. So 4, 5, 6 plus 6 is 12 plus 13 is 25. Yeah. So I have here a full question 5, question 6, question 7, and question 8. I have four full exam type questions, past year one, right? Provide with the answers as well. Okay, so let's just look at one of them. Just show you why it's called a design question. Okay, right. For example, question 5. Uh, where is the question? Is this wait question is zero, four. Uh, this is not the question. Oh, I see. The question is here. Question is here. Okay, that's the answer, not the question. All right, question is here. Yeah, cannot copy and paste this. Okay, let's just look at this one. So, for example, if you look at part A, miniaturized ubiquitous wireless sensor nodes are essential components towards building a smart environment. So if you want to make, you have a smart environment, smart building, smart factory, smart agriculture, all those smart environments. Why the environment is smart? Because you have some wireless sensors. So these wireless sensors, they are uh, collecting information automatically and then transmitting that information wirelessly. These are called wireless sensor nodes. They are the building blocks of IoT. Okay, so if you want to design a wireless sensor node, what is the standard capabilities that you must have for marks? What is the standard capabilities that you must have for a wireless sensor node? Okay, if you have a wireless sensor node, the standard capabilities that you must have inside is, first of all, you must have the microcontroller. The microcontroller is the processing element or a processor. Okay, but what are you processing? So you will need sensors. Okay, sensors. Sensors are used to take measurements. What are they measuring? So sensors are measuring physical changes in the environment. So depends on what you are measuring. Like you can be measuring light, humidity, temperature. So depends on what you're measuring, you choose the correct sensor. So the sensor measures physical changes in the environment and sends the information to the microcontroller for processing. So what does the microcontroller do with that information? The microcontroller will send that information to a wireless module, right? You must have a wireless module. The wireless module will then transmit this information, to the gateway, the local gateway. So you are setting up this wireless sensor network, let's say in your factory. So in your factory, you will have a gateway. So the gateway is the device that connects to the internet. The gateway is normally a computer. So this computer, it will collect all the information from the sensors, right? And then send them through the internet. It's better than putting internet capability on a small low power sensor like this. Okay. So small low power sensor is better you put a simple wireless module like a Bluetooth low energy or a simple RF transmitter receiver rather than an Ethernet fully Ethernet capable. Okay, and then so we need standard capabilities of 4 marks. So we got the first capability is sensing, processing, communication. You need one more. One more is power management. Wireless sensor nodes, they are very small and they run on normally battery power or energy from the environment like solar powered. Okay, so they will power everything in your system, and this is the most important because without power you can't run. So power management now, you will be getting some power. So power source, the power source can be battery or it can be renewable, meaning that you are generating power from the environment. So these are the 4 main components that you must have in an IoT device, right? In order for it to work, the four blocks, if you say block diagram. Okay. So then, second one. Okay, so I'll stop here. The second one. Briefly assess the suitability of embed platform. Embed is, for example, your LPC 1768 is a embed. Okay. For wireless sensor node development, justify your answer. So how to answer this? How to see whether embed is suitable for WSN or not. So we have to look at what is embed, right? So we just do a quick search. We just do a quick search. Do a quick search on embed. Okay, we just do a quick search on embed, and there you have it. That's your answer. Okay, that's your answer. Embed. So I copy this and I paste it here. Embed gives you a free open source IoT operating system with connectivity. So you got your internet library, Ethernet libraries, you got security. Security is you can encrypt and decrypt your information before you send it out of your serial port. You got storage, you got libraries to access USB, flash, all those non-volatile memory like SD card, device management. You can connect to USB or some other commonly used devices. Machine learning. Oh, the embed also provide you with machine learning library. You can do all those neural CNN, ANN, all those neural networks. They even provide you with libraries to do this. So you don't have to write the code. Just use the library. APIs, high level programming. Okay, so you can build your IoT product, build your WSN with all these free development tools, code examples, and support with hundreds of development bots. So this is your answer. Okay, where were we? Here. So, question. Briefly assess the suitability of embed platform for wireless sensor node development. So embed platform, blah, 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 blah. That's your answer. Okay. Right. So this is example of open-ended design question. And in fact, the open-ended design questions are the easiest questions because as long as your answer is justifiable, is uh, is logically correct, it will be accepted. Okay. Can we copy paste answer from online? If you can find it, lah. Nowadays I don't ask questions where you can find the answer online one. It so happens that this question, you can find the answer online. That's why I paste it because I'm lazy to type. Okay, but so I don't think you can find because uh, now the exam questions are all open-ended. So the questions will all be you don't have state describe all this one. No more already. No, you don't have this type of questions anymore. Nowadays the questions you see in your exam paper will be apply, analyze, uh, design, this type of question. So all of this is you are given some situation, then you have to understand, analyze the situation, and then apply your knowledge to come up with some answer. So you can't find your answers from books or internet already. Okay, or very difficult. It won't be a direct question where you can just Google and copy and paste an answer. Okay, so that's why I stress again, this round your final exam, very important that you must understand all your classes, all your lecture, all your classes that you must understand to be able to answer. All your subjects also, I think it's like that. Okay, so but don't worry, next week we will have a revision. Okay, next week our 3-hour lecture we will revise. We have a revision on your these 4 different topics. Okay. I don't understand about the last question. Why high priority thread will be blocked by low priority thread since high priority can preempt low priority? That's because ayo, I deleted my answer. Okay, that's because uh why yes, high priority. The low priority thread, right? The low priority thread has obtain the semaphore to a shared resource. Okay, the low priority thread has obtained the semaphore to the shared resource already. So it is using the shared resource. Now, then, then a high priority thread is triggered to run because of some interrupt. Some interrupt has triggered a high priority thread to run. Okay, and the high priority thread the high priority thread needs needs to use needs to use the shared resource. Okay, but how cannot because yes, the high priority thread is triggered to run, so it preempts the low priority thread and runs, right? But the high priority thread needs to use the shared resource. Okay, uh, but the the semaphore has already been obtained by the low priority thread. So the high priority thread really cannot run already. The high priority thread must wait. So the high priority thread must wait for the semaphore to be released by the low priority thread. No other way. No other way. The high priority thread must wait for the semaphore to be released by low priority thread. So okay lah. So when you're designing this system, you must take into account this problem. So you don't make the low priority thread so long. So the low priority thread, after it finish using the resource and release the semaphore, the high priority thread can still fulfill its deadline. So okay, no problem. But what we didn't account for was the low priority thread being blocked by a medium priority thread. So then that makes it life very difficult for the high priority thread already. So for cases like this, whenever the high priority thread needs to use a shared resource that is being blocked by a low priority thread, the common solution is just to temporarily raise the priority of the low priority thread to high priority so that the low priority thread can immediately run and complete and release the shared resource, release the semaphore so that the high priority thread can then continue its execution because it's waiting for the semaphore. So is that okay, Kashi? Okay, right. All right, class. So I recommend that you start doing your revision. All right, since we have completed the syllabus already, so you should start to intensively do your revision. And then next week during our consultation sessions, the lab practical sessions are used as consultation. You can refer to me for anything that you don't understand. So I'll be there I'll be in the Google Meet during the lab sessions. And we will have revision for our 3-hour practical lecture class next week. Okay. So, all right. Thank you everyone for coming today. We will stop here and have a nice weekend, everyone.